morning, students. Today we will learn another interesting specialized kind of a linear programming problem, which is called as the goal programming problem. As the name indicates, in this kind of a linear programming problem, a goal is specified before solving the problem, and the linear programming problem has to be solved in such a way that that particular goal is achieved. The outline of today's talk is as follows. First of all, we will consider an example of the goal programming problem. Then we will try to solve the problem with the graphical solution. Then we will obtain the solution using the simplex method. Then we will define what exactly do we mean by a linear goal programming problem. After that, another definition, which is for the multi-goal programming problem. And then we will look at the weighted sum method and the pre-emptive method, and finally an exercise. So let us begin. Here is an example of a real life situation. Suppose a factory can manufacture two products A and B. The profit on 1 unit of A is rupees 80 and 1 unit of B is rupees 40. The maximum demand of A is 6 units per week and of B is 8 units per week. The manufacturer has set up a goal of achieving a profit of rupees 640 per week. We are required to formulate the problem as a goal programming problem and solve it. Now, as you see in this problem, the profit of rupees 640 per week has been specified by the manufacturer before solving the problem. Now, coming to the solution of the problem, let us define two variables x1 and x2 as follows. Let x1 be the number of units of A to be produced per week. Similarly, let x2 be the number of units of B to be produced per week. Also, let F denote the profit. Then, as before, the expression for the profit F can be written as 80x1 plus 40x2. Also, the goal is 640 rupees. Now, F, that is the profit, may exceed the goal of 640 or may fall short of it. So, these are the two possibilities, and the third possibility is that it may be exactly equal to 640. So, let us try to visualize all these situations with the help of defining variables. So, therefore, let U and V be two variables which are defined as follows. Let U greater than or equal to 0 denote the shortfall, that is the underachievement of the goal. Similarly, let V greater than or equal to 0 be the excess or the overachievement of the profit from the goal. Now, as I said, there will be three possibilities that could exist. The cost will be as follows. The goal will be as follows. The goal will either be exactly achieved, This will happen when u and v are both equal to 0. The second possibility is the overachievement of the goal, that is, u is equal to 0 whereas v is strictly greater than 0. The third possibility is the underachievement of the goal. In this situation, u will be strictly greater than 0 whereas v will be exactly equal to 0. So, only these three situations are possible. Therefore, only those solutions of the linear programming problem are acceptable in which at least one of the variables u or v is 0 or both of them are 0. Therefore, either the value of f should be equal to 640 minus u or the value of f should be 640 plus v. Now, if we combine these two conditions, we get one consolidated condition as follows: f is equal to u minus v f plus u minus v is equal to 640, where at least one of the variables u or v are 0. So, this condition f plus u minus v is equal to 640 should be taken along with the condition that at least one of the variables u or v should be 0 or both of them should be 0. Now, in order to achieve the goal as closely as possible, the objective should be to minimize the deviations from the goal. This will be possible only if we minimize the deviations from the goal. Therefore, let us set up another objective function, and this will give rise to the problem formulation: minimize the deviations. That is, minimize, let us denote it by capital F, is equal to u plus v subject to the conditions 80x1 plus 40x2 plus u minus v is equal to 640, and x1 is less than or equal to 6, x2 is less than or equal to 8, and all the four variables x1, x2, u and v should be greater than or equal to 0. We have to ensure the conditions that either u or v or both should be equal to 0. This is the problem formulation for the given problem. Next, let us try to solve this problem first with the graphical solution. Now, in the graphical solution, we assume that for the moment we will plot on the horizontal axis the x1 variable and on the vertical axis the x2 variable. And if you plot this constraints x1 less than equal to 6 and x2 less than equal to 8, you get this rectangular shape, and the straight line, the first condition, let me go back, the first condition, the first constraint 80x1 plus 40x2, for the moment if you ignore u and v, then this is equal to 640. So, 80x1 plus 40x2 is equal to 640 can be plotted as follows. It is shown in the red color in the diagram, which is shown by joining the points D and E. Now, if you look carefully at this diagram, here we have ignored the u and the v variables. Only the x1 and the x2 variables have been considered. But if you look at the line segment DE, all the points on the line segment DE have both the values u and v is equal to 0. This has been explained in this slide. Considering the function f is equal to 80x1 plus 40x2, we find that on the line DE, as shown in the red color, the value of f is equal to 640. Thus, the goal can be exactly met by choosing x1 and x2 such that x1, x2 lies on the line segment DE. Now, let us come to the points on DE. For points on DE, u and v are both 0, giving the minimum value of capital F. That is, all the points on the line segment DE, the goal will be exactly satisfied. The second situation arises if the points x1, x2 falls in the region denoted by DEC. This is shown by the peach colored area. In this region, the profit is over and above 640. This indicates by the variables u is equal to 0 and v is strictly greater than 0. The third situation arises if x1 and x2 fall in the region OADEB as shown in the purple color of the diagram. The points in this region is less than 640, which is indicated by the variables u is strictly greater than 0 and v is equal to 0. Now, let us try to solve the same problem with the help of the simplex method. The reason why I have taken this particular example is to illustrate vis-a-vis the graphical solution what happens in the simplex calculations. Because this was only a 2-variable problem. However, when a larger sized problem is encountered, then it is not possible to solve with the graphical method. Therefore, we will have to solve it with the simplex method. So, coming to the simplex formulation, the formulation is as before: minimization of capital F is equal to u plus v subject to 80x1 plus 40x2 plus u minus v is equal to 640. X1 is less than or equal to 6 and x2 is less than or equal to 8, and all the 4 variables x1, x2, u and v should be greater than or equal to 0, such that either u or v or both are equal to 0. So, in order to solve the problem, we first need to convert the problem in the standard form. Therefore, we need to add slack and surplus variables, and this is what the formulation looks like. Minimization of u plus v subject to 80x1 plus 40x2 plus u minus v is equal to 640, and the second constraint becomes x1 plus x3 is equal to 6 Here x3 is a slack variable because this was a constraint of the less than equal to type. And similarly, the third constraint becomes x2 plus x4 is equal to 8, and of course all the 6 variables x1, x2, u, v, x3 and x4 should be greater than or equal to 0, with the condition that either u or v or both are equal to 0. Now, when we solve this problem with the simplex method, we have to be very careful, because we have to perform the simplex calculations, making sure that at any iteration u and v do not enter the bases together. Either u should enter the bases or v should enter the bases. So therefore, we have to make sure that in the entire simplex calculations this condition is hold. In this table I have illustrated the simplex calculations, and as you can see that at each iteration we are getting either one of the variable u or the other variable v into the basis, and at some iterations both of them have left the basis. The idea is that u and v should not enter into the basis together. So therefore, in the first iteration we have the basis as 0, u, x3 and x4, similarly u, x1 and x4, and finally x2, x1 and x4. So this indicates that we have to perform the simplex calculations as before, only making sure that the conditions on u and v should be followed. Now, if you look at the last table, the final table, you find that the condition for multiple solution is holding. And what is the condition for multiple solution? It is that the deviation entries corresponding to the non-basic variable is 0. So here you can see that this entry corresponding to the x3 variable in the deviation row of the final table is 0. This is an indication that the problem has multiple solutions. So what we need to do? We need to perform another iteration to get the other multiple solution. So the solution is x1 is equal to 6, x2 is equal to 4 with z is equal to 0. This corresponds to the point D in the diagram. So if you look at the diagram, the point D given by 6, 4 is the solution what we have obtained using the simplex method. But the optimal table indicates that this is the case of multiple solutions. So we need to perform another iteration. And we find that when we perform another iteration, we get another solution. And what is that solution? This solution is shown in the second iteration of this slide, which gives us the answer as follows. That is, the alternate solution is x1 is equal to 6 and x2 is equal to 4 with z is equal to 0. This corresponds to the point E given by 4, 8 in the graphical solution. Therefore, the problem has multiple solutions, namely all points on the line segment D and E. On the line segment D and E, U is also 0 and V is also 0. So, on all points of the line segment D and E, the goal is exactly satisfied on all the points of the line segment DE, and this matches with our graphical solution. So the goal is exactly achieved on all points of DE. Of course, using the simplex method, it is difficult to identify the underachievement and the overachievement solutions. So once we have finished with this example, now let us try to generalize the definition of a linear goal programming problem. It can be written as follows: minimization of capital F is equal to U plus V, where U and V are the underachieved and the overachieved variables, and this should be subject to Fx. This Fx is nothing but the objective function of the problem that is given, plus U minus V is equal to G. G is the goal, and this is subject to the conditions summation of Aij xj is equal to Bi, where I goes from 1 to up to m, and U V xj greater than equal to 0, where j is equal to 1 to n, with either U or V or both equal to 0, where U is the underachievement, V is the overachievement, and G is the goal. This describes the most general linear goal programming problem. Now, in reality, there may be a possibility that there are multiple goals of the problem. What does this mean? Suppose the linear objective functions in a problem are p in number. So, suppose there is one objective function, let us say f1x, another objective function f2x, another objective function fpx. So, there are p objective functions, and each of the objective function has a different goal. So, let us try to denote the goals by gk, and the value of k goes to 1 to up to p. So, we want that each of the objective function fi should reach the corresponding goal gi as closely as possible. Of course, the constraints will be all common to all the objective functions. So, what are the constraints? They are the usual constraints: summation Aij xj equal to Bi, and of course, the decision variables xj should be greater than or equal to 0. Now, let us denote by ui the underachievement variables, and similarly vi the overachievement variables. Then we can denote p number of equality constraints as before, that is fkx plus uk minus vk is equal to gk, where the value of k goes from 1 to up to p, and uk and vk should be greater than or equal to 0, such that both uk and vk are not non-zero together. Now, the question is, what should be the objective function of the multi-goal programming problem? So, can you guess? Yes, it is similar to the case of the single goal programming problem. All you need to do is club together all the UKs and the VKs and take their summation and minimize them. So, therefore, the weighted sum approach tells us that we need to minimize f is equal to summation pk uk plus qk vk, where pk and qk are the corresponding weights that you would like to assign to each of the UKs and the VKs. Of course, it is subject to the original conditions, the P conditions that we are talking about, that is fkx plus uk minus vk is equal to gk, and the conditions of aij xj is equal to bi, I is equal to 1 to m, xj should be greater than or equal to 0, j is equal to 1 to n, and uk and vk should be greater than or equal to 0, such that uk and vk are both not non-zero together. And as I said, pk and qk are suitable non-negative coefficients which indicate the priority that should be assigned to the underachievement and the overachievement of the goals gk set for the objective functions fjx. That is, you are given the freedom of assigning suitable weights to each of the objectives. Next we have the pre-emptive method. Here in this method we assign each deviation variable an order of priority. That is, we want to say that each variable should be given different priority depending upon the user. Corresponding to each priority, form an objective function which is the sum of all the deviation variables having the same priority. Then we have as many objective functions as priorities. In the simplex calculations, we carry out each objective function in a separate row and arranging them in order of their increasing or decreasing priorities. So, the same calculations can be rearranged in the simplex calculation corresponding to each of the objective functions. Then, by the simplex method, first minimize the objective function with the highest priority, then try to minimize the objective function with the next priority, if it is possible to do so without disturbing the optimal solution of the problem. Otherwise, leave it as it is and move on to the next objective function. So, let us now take another example. Suppose a company produces two products A and B, both of which are manufactured on the same plant. The production rate for each product is 1 per hour. The operational capacity of the plant is 80 hours per week. The estimated maximum sales per week for the product A and B are 70 and 45 respectively, and the production is not to exceed these figures. In order to meet the market demand, the company can run the plant overtime, which may be around 10 hours per week. Net profits from the sale of A and B are in the ratio of 5:3. The company has listed the following four goals in order of priority: P1, P2, P3 and P4. The first goal P1 is keep underutilization of the production capacity as low as possible to avoid retrenchment of workers. Similarly, the second goal P2 is overtime operation of the plant to exceed 10 hours as little as possible. The third goal P3 is shortfall in production of 70 items of product A and 45 items of product B to be as low as possible. The profits on sale of A and B being in the ratio of 5:3, the priorities of keeping the production of A close to 70 and that of B close to 45 may also be taken in the same ratio. And the last goal, P4, is keeping the overtime operations of the plant as low as possible. So let us now try to model this. Let x1 and x2 hours of plant time per week be used for production of A and B respectively. Since under or overachievement of the normal production capacity of 80 hours per week is allowed, therefore, we have a constraint x1 plus x2 plus u1 minus v1 is equal to 80, where u1 and v1 are the deviation variables indicating underachievement and overachievement respectively. Then the production per week of A and B is not to exceed 70 and 45 respectively. Since it takes 1 hour of plant time to produce one item of A or B, therefore we have the conditions x1 plus u2 is equal to 70, x2 plus u1 is equal to 45, where the variables u2 and u3 are shortfalls in the achievement of the production goal for A and B respectively. Then the overtime running of the plant may be about 10 hours per week. That is, the total running time may be more or less 90 hours. Hence, we have a condition x1 plus x2 plus u4 minus v4 is equal to 90, where u4 and v4 are the possible deviations from this goal. Therefore, the constraints of the problem look like this: x1 plus x2 plus u1 minus v1 is equal to 80, x1 plus u2 is equal to 70, x2 plus u3 is equal to 45. Then the fourth constraint is x1 plus x2 plus u4 minus v4 is equal to 90, and all the variables x1, x2, u1, v1, u2, v2, u4, v4 should be greater than or equal to 0, such that the conditions ui, vi for I is equal to 1 and 4 should not be 0 simultaneously. Now, using the weighted sum, we can tabulate the priorities of the goal in this table. In the first column, we have the priorities of each of the 4 goals, and in the second column, we have the corresponding decision variables, and finally, in the third column, we have the corresponding weights of these goals, priorities. As you can see, P1 has a decision variable u1, and let us assume that its weight is 10. Similarly, P2 has the decision variable v4, and let us assume that its weight has 8. Similarly, P3, it has two variables U2 and U3, and they have their weights as 5 and 3, and the P4 has the decision variable V1 and it has weight 1. So, combining all these information into one, we can frame the objective function as f is equal to 10 times U1 plus 8 times V4 plus 5 times U2 plus 3 times U3 plus V1. So, this is the overall objective function of this problem. So, using the preemptive method, we can say that P1 has F1 is equal to U1, which is equal to 80 minus x1 minus x2 plus V1. P2 has F2 is equal to V4. P3 has F3 is equal to 5U2 plus 3U3 is equal to 485 minus 5x1 minus 3x2. P4 is equal to F4 is equal to V1. The first minimum F1, first of all we will minimize F1, then we will try to minimize F2 without disturbing the minimality of F1 and so on. So, we will keep on retain the minimality of the previous function so that the next one can be minimized. So, at the end, now I would like to give you an exercise. An electronic firm produces two types of TV sets. Production of either type requires the same time. The firm has a normal production capacity of 40 sets a week. The maximum number of sets of type 1 and 2 that can be sold per week are 24 and 30 respectively, and the profit on them is rupees 800 and rupees 400 per set. The firm has set up a goal of earning rupees 24,000 per week. Solve the linear goal programming model, and can the firm overachieve its goal? If so, up to what extent? Now, the answer to the problem is written here. It is minimize u plus v subject to 800 x1 plus 400 x2 plus u minus v is equal to 24,000 subject to the conditions x1 plus x2 less than or equal to 40, x1 less than equal to 24, x2 less than equal to 30, and x1, x2, u and v should be greater than or equal to 0, and u and v are not simultaneously non-zero. The solution to the problem is 24, 12 or 20, 20 or any convex linear combination of these 2 points. The firm can overachieve its goal up to rupees 25,000 by producing 25 color and 16 black and white TV sets. So, like this we have illustrated that we can formulate a multi-goal linear programming problem or a single goal programming problem depending upon the requirement of the problem. Thank you.